Assalamualaikum dan salam sejahtera. Today we continue our lecture about hardy cross method, and just a repetition from the previous class. So this is how we simplify the idea of losses here. So we have the major loss equation FL over D V square over 2G, and then we substitute with the idea of flow rate here by replacing the V square here with the flow rate Q, and then we found that all this term is actually a constant. So we rewrite our equation for the losses as KQ square. So and then as we know, we will calculate the losses. So if our prediction is correct, means we manage to balance the losses. So means the total losses for clockwise and counterclockwise need to be balanced. It must be equal. So if our assumption is not correct, so means we need to deduct a small amount from the clockwise, and then we put that amount, that delta Q, in the counterclockwise calculation. So and then if we expand the terms, expand the equation of this one, and then we neglect the small amount of delta Q square, so we could have this term, and then we replace with the losses is equal to KQ square, and KQ is equal to losses over Q. Finally, we could get the equation of this one. So and then this is actually the value of delta Q. So and then what we need to do is we just use the value of delta Q to determine whether we need to stop our calculation or not. So the best one is we get the value of delta Q is equal to 0. But however, if you cannot manage to get delta Q equal to 0, please do again and again until the value of delta Q is very, very small. So again, the delta Q is not the final answer. You need to do something with your final delta Q to give the final answer. So let's say we have an example of this one. For example, we have the pipe network like this one. So for example, we have one station here, and then it's flow to another station, and then it create network like this one. So and then from here, the input is 100 liter per second. We have two output here, which is one is 25 liter per second, and the other one is 75 liter per second. So the losses for each pipe is given in this diagram. So we have K equal to 1, K equal to 2, 3, 2, and 1 here. So this is just for practice. So we give you a small number of K. In final exam or in test, maybe I will give you some a big number of K, or you need to calculate the value of resistance, the value of losses by using the equation of F L over D V square over 2G. Okay, so here it is okay for you not to change the unit here. So it is okay for you to maintain liter per second, because we are doing the ratio, actually the ratio calculation. So means if the inlet is in liter per second and outlet is also in liter per second, it is okay for you not to change into meter cube per second. So and then normally we will use liter per second, because liter per second is quite precise compared to meter cube per second. So what I mean by precise is, for example, people talk about 0.01 liter per second. So if we convert this into meter cube per second, maybe you will have 0.000001 meter cube per second. So means it will give you a very small number here, but it's still actually will complicate your calculation later on. So normally we will use liter per second to solve this problem. So and then before we solve it, okay, please read this basic step. So what you need to do is you need to determine loop or cycle first. So what is the meaning of this one is you need to identify what looping or what cycle that we could assume in the diagram. So for example, for this one, so we will have this loop, mean this closed section, and we will have another one here. So here we could say that we will have two loops of pipe system. Then the second one, number 2 here, we need to predict the initial flow rate, because the question is we need to determine the distribution of flow rate. So mean we need to determine what is the flow rate at here, 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 and here. So means we have 5 pipes. So we need to determine 5 flow rate. So in this situation, what you need to do is you need to predict. First, you need to predict what is the flow rate at this pipe, and all the pipes here. So, and then you need to fulfill the Hardy-Cross method. So I will show you later. And then you need to redraw the figure and propose your new flow rate. So here, please make sure that you are not give me the value of delta Q, because the value of delta Q is not the answer. So delta Q is actually just an indicator to show whether our result is good enough or we need to do another calculation. So, and then if your delta Q is not very small, it's not small, you need to repeat step 1 until 4 until your delta Q is approaching 0. So, and then after you get the delta Q, again, the delta Q is not the answer, but you need to propose your new flow rate as your final answer. So this is the basic step, and I will show you how to solve this problem. Okay, so for example here, we determine the loop. So for example, we assume that this is our loop 1 and this is our loop 2. So to ease our calculation, we assume that clockwise is positive and counterclockwise is negative. So, and then we need to predict the flow rate. So for example, so the inlet here is 100 liter per second. So it's split into 2 here. So let's say I would like to predict the flow rate for A to B here is 60 liter per second. So, and then the flow rate here must be 40 liter per second. Why? Because the inlet is 100 liter. So when it's split into 2 branches here, so the total of outlet here must be 100. So 100 here, so it must be equal to 60 plus 40. So, and then at this junction, okay, so it's split into 3. So we have here, we have this direction, and we have this direction. So again, we need to predict the flow rate. So this is the output, and it was written as 25 liter per second. So means that here in these 2 branches here, so I predict one is 20 liter and another one is 15 liters. So means that the total of 60 liter per second here is equivalent to 25 times 20 plus 20 and plus 15. So the total of output is remain 60 liters. So, and then at this point, so we found that the output is here, but it received 2 input from here. So mean it received 40 plus 15. So the total must be 55, because these two inlet, okay, must contribute into this outlet 55. So, and then at this point we have outlet like this one. Okay, and then this will become the inlet. So here this 75, so it is equal to 20 plus 55 here, so the output will become 75. So after you manage to predict the flow rate, at the same time you need to make sure that the inlet and outlet must be conserved. So means the total inlet must be equal to the total outlet. So after you check all that one is correct, and then we could fulfill the equation. Okay, so we create a table here. So we know that the branch AB, AC, BC, CD, and BD. So we list down the value of K. So and then we list down the predicted flow rate, and then we could calculate the losses here. So HF is equal KQ square. So uh, as our example is, we have a 40 here. So 40 times 40 is 1,600, and then we times 2 here, so we will get 3,200. So and then we make another table to fulfill our Hardy-Cross method equation here. So the equation is like this. So we have delta Q is equal HFC minus HFCC and 2 sigma HFCQC HCCQC. Okay, so let's do this one. First, we need to understand that sigma here means summation, means the total amount. Okay, so we do this. Okay, first we need to solve this term, means the upper term here. So we have the sigma for clockwise minus the sigma for counterclockwise. So here, for example, if we see this one, so we have the value of A here. Let's say we start here. So and then if we go here, so the flow rate direction here is actually same direction with the looping direction here. So means that this must be a positive one. So here we write 3,600 plus, so we have 3,600, and then we have plus the 15 liters here, BC here. If we see here, BC is 675. So we plus with 675, and then we have this flow. So this flow, we found that the direction of this one, okay, the direction of this one is reverse. Okay, it's not parallel, it's not the same direction with the looping here. So means that it will carries the negative sign. Okay, so this is what we mean by this one. So and then if we add everything, so we have 1,075. Okay, so and then for the lower terms here, so we just add the losses and the flow rate. So we just add, we have a losses here. Okay, we have a losses here, here, and here. So we have a 3,600 divided by 60, 675 divided by 15, and 3,200 divided by 40. So times 2, so we get it is 370. So later on, then we divide 1,075 with 370. So we get 2.91. So this value is actually the value of delta Q. So the value of delta Q here and also the value of this one, it is okay. If you get negative or you get positive, both are okay. So no need to correct them. Just carry on the calculation, and then sometimes you will get the value of delta Q here negative. So it's still okay. So and then we try to solve the second loop here. So again, we'll see how we solve the idea of this one. So we start with the 800. So 800, if we see here, is actually the BD. So the BD here, okay. So because the direction is the same direction with the loop, so we have positive. So here, the direction here is reverse direction with the loop, so we have negative, and the direction of the loop here is also reverse from the loop direction here, so we have another negative at this point. So that's why we write here, we calculate 800 minus 3025 and minus 675. So we get negative 2900. So it's okay to have negative value. So and then to fulfill this one, we calculate, we just add the losses is 800 divided by 20. So we could see here 800 divided by 20. And then we will have 3025 divided by 55. So we have 3025 divided by 55 and 675 divided by 15. So we have this one, and then we have it is 280. So and then we get the value of delta Q here is negative 10.36. So here, how to determine the value of delta Q here, it is acceptable or not. So we are aiming to get value of delta Q is actually less than 1 liter per second. So if you get 2.91, so you need to do your second trial, so or your second iteration to get another delta Q and to propose new flow rate. So again, your calculation actually cannot stop here because it still not give you a big marks. Okay, as I said, the value of delta Q here is not the final answer. So what you need to do is we need to rebalance, or we need to propose the flow rate based on the value of delta Q here. Okay, so the modification of flow rate value need to be done based on the value of delta Q calculated above. So modification means you add or you subtract the value depends on the depends on this rule. If it is clockwise, so you need to subtract minus with delta Q. If the rotation or the flow is counterclockwise, so you need to add with delta Q. So it is actually the idea is clockwise, you need to deduct minus. So if you see the determination here, clockwise is positive. That's why after you get delta Q, you need to reverse the process. So if we get clockwise, we need to subtract the value. Okay, so how we could manage this? Okay, we need to see the loops here. So for example, from here, so we have the flow here, which is the clockwise. Okay, so means that we need to minus with the value of delta Q. So we need here, as I said, the AB here is minus. So and then the AC. Okay, if we see the AC here, okay, so the flow is actually counterclockwise. So it must be add. So here, if we see, so we have add here. Okay. So and then we leave the value of BC here later on. So we focus on CD, for example. So CD here, we have a CD here. So the flow is from C to D. So it's reflect rotation like this. So it means the counterclockwise. So we need to add the value. So and then for BD, so it is start from here to here. So means that the flow is actually clockwise. So we need to deduct. So we need to subtract the value. So how about BC? So BC here is actually a very unique junction because it stays in the middle. So and then it share with loop 1 and loop 2. So what we do is actually we need to calculate both sides. So for example here, the flow is like this. So and then this flow will create clockwise for loop 1. But this direction will create counterclockwise for loop 2. So means that for loop 1, we need to subtract, and for loop 2, we need to add. So mean here in the table, so for clockwise, okay, so and then we need to subtract, and for counterclockwise, we need to add. Okay, so this is the idea of this table. Okay, how to add and how to deduct that amount. Okay, for example, for AB and AC here, so we are using delta Q from loop 1. So this is the value of delta Q from loop 1. So we have loop 1 here. So and then the value is 2.91. So and then if negative, so what we do, we deduct the value of 2.91 from the predicted flow rate. So the predicted flow rate is 60. So we minus 2.91, so we get 57.09. So and then here we add with the 2.91, so we have 42.91. And here for for clockwise here, we need to subtract. So we minus with 2.91, but we need to add with negative 10.36. So we have 1.73. So here we need to add with negative 10. So we will get 44.64. And here we need to minus. We need to deduct with negative 10. So mean it will become add. So and then it will give us 30.36. So actually, this is your final answer. So this flow rate is actually you need to submit as your final answer. However, this still will not give you a full mark. So what you need to do is you need to redraw the diagram, and then you need to write your proposed flow rate at the junction here. So if you write this with a correct flow rate here, so you will get full mark. If not, so a lot of mark means it is difficult for you to get full mark. Okay, however, because in our calculation here, we found that the delta Q here is not equal or less than 1 liter per second. So means that we need to do our second trial. So how to do the second trial? So again, it is the same. After we propose the new circuit like this, so and then we could start to have our second table. So means that first we need to make sure that the continuity equation is fulfilled. So mean that 57.09 plus 42.91, so it will give us 100. So and then this value, it is equal to 25 plus 30.36 and 1.73. Okay, so actually here if we have something, you need to make sure that the value is correct. For example, so 0.36 plus 73, it will give you 0.9. So please make sure that the number here is totally correct. So and then these two value, okay, will equal to this value 44.64. So we have 1.73 plus 42.91. If you add these two value, it will give you 44.64. And then these two value, if you sum these two values, so it will give you 75. So please make sure first your flow distribution is equal. Okay, for example, because in this calculation maybe so you are not very careful, so might be your answer is in 3 decimal place and another one is in 2 decimal place. So means that at this stage you cannot balance the flow. So what you need to do is you need to change manually. So I mean for example here, for example, in your calculation, so the value here is 44.62, for example. So, but the total of this value is 44.64. So, means that you need to uh, delete this value, and then you need to use the new value. So, means that again you need to balance the inlet and the outlet to be correct. So, and then this is the starting page for your second trial. So, mean by using this equation, by using this value, what you need to do is, again, for example, we have a 57.09. So, means that we create table here. So, the value of AB here is not 60 anymore. It will become 79.09. That's 57. So, it will become, okay, it will become 57.09. So, and then you replace all of this with your new flow rate, and then you start your the value of losses here, and then you start to calculate like this one, and then you see the value of delta Q. So, and then by using this delta Q, okay, you proposing the second trial flow rate. So if the value of delta Q here is still bigger than 1 liter per second, 1 liter per second, so you need to start your third trial. So this is actually the way Hardy cross method are being conducted on paper.